Man has always been a builder. Yes, man has always been a builder, but his structures have endured only when the materials he used were able to resist the forces of nature. Most of those forces we have found it easy to comprehend. The wind, the sun, the rain, and the snow. So understanding them, we have built our shelters against them. Simply at first, then as we acquired new skills and imagination, with increasing comfort, grace, and beauty. And with each advance, we might say to ourselves, this is good. This is beautiful. And this is durable. But always as we built, we took one thing for granted: the earth beneath our feet, the solid earth in which our structures were anchored. But the earth cannot be taken for granted. For sometimes in unexpected places and without a moment's warning, our seemingly solid earth will heave and twist and strain, wrenching our homes in its violent spasm, filling our minds with helpless fear. Leaving behind its hideous desolation. Desolation we have seen so many times and in so many places. San Francisco, Seattle, Santa Barbara, Long Beach, Helena, Manila, Tokyo, Tehachapi, Arvin, Bakersfield, and countless others around the world. Where next? Where no? We can only guess. If this be our fearful threat, where then shall we find our answer? We found our answer in the earth itself. For while the earth may tremble and quake beneath our feet, it also yields the rich ore from which we take our iron. Out of the iron we make our steel. And out of the steel we create the strength to support our buildings. Yes, even against the shock of earthquakes. For while the earth's shock can play havoc with those buildings which are poorly designed or built of insubstantial materials, there have been many examples that structures built of steel or reinforced with steel have been able to withstand the shock of earthquake. One such example was the famous old ferry building of San Francisco. Framed with steel, this venerable landmark was one of the buildings to survive the earthquake of 1906. With but minor damage to the tower. In the Pacific Northwest, a convincing example was the Smith, which, with its steel construction, withstood the earthquake of 1949. In Long Beach, California, the beautiful Villa Riviera, constructed of steel, was a notable survivor of the earthquake of 1933. And in Arvin, California, the Arvin High School, with its modern steel-reinforced construction, suffered only minimum damage in the severe Tehachapi shocks of 1952. What a contrast to the Cummings Valley School, not far away, which, lacking such strength, was reduced to rubble by the very same earthquake. One does not like to think of children trapped in a collapsing schoolhouse. From such convincing evidence, we have the proof that steel is an important factor in the construction of earthquake-resistant buildings. But in order to understand why, we must know something about the nature of earthquakes themselves. To begin with, movements of some kind are going on in the Earth's crust somewhere all the time. Movements which, in their own way, are as restless as the changing tides of the sea. Many of these movements are so minor that we ourselves do not feel them. but we know they're going on because our sensitive recording instruments constantly tell us so. On the other hand, there are movements so strong and violent that we do feel them, and very sharply. Many of these movements have taken place along the Pacific coast, a region which, to many people, has become known as the earthquake belt of North America. Let it not be assumed, however, that earthquakes are confined to this so-called earthquake belt. Actually, earthquakes have occurred in every state. The strongest shocks of record in the United States occurred in 1811 and 1812 in Missouri. Another earthquake, originating in South Carolina in 1886, was felt 1,000 miles away. Earthquakes are no respecters of locality. They occur because of some slipping or rupturing within the earth, and this produces a fault. Sometimes these faults are even visible on the Earth's surface, such as the famous San Andreas Fault in California. It was the slipping along this fault which caused the San Francisco earthquake of 1906, and several later ones as well. Sometimes, too, an earthquake may cause cracks or fissures at the Earth's surface. At one location, the Tehachapi quake of 1952 created a crack nearly 6 feet wide and 6 feet deep, a surface indication of some rupturing deep below. And it is there that our story lies. The Earth, as we generally understand it, has 3 layers: the outer crust, the mantle, and the core. The outer crust upon which we live has an average depth of 20 to 30 miles. Beneath this crust is the mantle, extending to a depth of about 1,700 miles. And beyond the mantle lies the core, extending about 2,150 miles to the center of the Earth. Now, as already mentioned, we know that movements are taking place constantly in the Earth's crust and mantle. As the movements continue, stresses are built up, until at some weak point, the Earth's crust is overstressed, and a sudden shearing or slipping failure occurs. It is the sudden release of stress by the slip that produces the earthquake. From this subterranean rupture, vast amounts of energy are released, which radiate in all directions through the Earth's crust, mantle, and core. These radiations are called seismic waves. By studying these waves, we learn much about the origin and intensity of the earthquake shock. Such studies are made at seismological laboratories located at strategic points throughout the world, where seismic waves, whenever they occur, are scientifically recorded on sensitive instruments known as seismographs. The various seismological laboratories, by pooling their information, can trace the origin of the shock and plot the degree of strain caused by the earthquake as well as its aftershocks. The seismograph is but one of many delicate instruments which tell of movements in the Earth's structure. One unique instrument, for instance, has been installed in a tunnel under the San Gabriel Mountains of Southern California. A device so designed as to measure long-term strains in the Earth's crust. As these strains accumulate, the resulting movements, too slight to be seen with the naked eye, can be measured and recorded. And it is hoped that such findings may make it possible someday actually to forecast when and where earthquakes will occur. Also, a special type of seismograph, so sensitive a breath can set it in motion, is used to measure the actual movement at the Earth's surface during an earthquake and its aftershocks. With data gathered in this and other ways, scientists are able to recreate the movement and behavior of earthquakes long past. For example, a mechanical device which simulates the ground motion of the Long Beach quake of 1933 is used to illustrate how buildings react under varying loads. In addition to studying earthquakes which have actually occurred, scientists also learn from purely hypothetical quakes. At one California university, itself a victim of the 1906 earthquake, a mechanical test creating shocks of varying degrees of intensity helps to determine how structures will react to possible future earthquakes. This study is all the more significant because the test structure is an actual scale model of an actual building located at Bush and Montgomery Streets in San Francisco, the Alexander Building, a slender 16-story structure built on a framework of steel. Like its laboratory model, the building itself is furthering earthquake research. For sensitive instruments to measure accelerations due to shock have been installed in the building at several different levels. With the aid of these instruments, it is possible to study the building's reaction to the forces created by earthquake movements whenever they occur. These, of course, are only a few examples of many types of research going forward all the time. And we have learned from such research that different types of buildings react in different ways to earthquake shocks. These differences can be illustrated by comparing the reactions of a low structure, a tall, slender structure, and an L-shaped structure. In the case of the low structure, when the Earth's movement causes the base to move, the roof, because of its inertia, tends to lag behind and does not immediately follow the ground. Its weight, therefore, creates considerable stress in the members connecting the floor to the roof. The resulting strains, known as shearing strains, may cause the structure to collapse unless the members are properly braced and tied together. With a tall, slender structure experiencing the same ground movements, the building oscillates, causing various bends. Consequently, the frame must have sufficient flexibility to permit the structure to assume the distorted shapes. Without such resilience, the structure will suffer excessive damage. In the L-shaped structure, if the ground movement is parallel to one wing, this wing, because of its length, may have considerable resistance to the shock. But the other wing is broadside to the movement and consequently will deflect more. The unequal deflection between the two wings will cause a twisting action. And if the building is not properly braced and tied together, this twisting or torsion may cause failure at the junction of the two wings. Obviously, if buildings are to withstand these destructive forces, they must be constructed of suitable materials which will not fail. It is for this reason that steel and steel-reinforced materials have become the key